To show the inverse of a linear transformation, we need to follow these steps. The first one here is to come up with the standard matrix of the given linear transformation. Then, let's check if it's invertible. If the standard matrix is invertible. If it is, we can automatically say that the linear transformation of T is also invertible. And we can do that by solving for the product of your inverse times a certain vector, to which we will be discussing later. And after that, we're going to come up with now its inverse, or the definition of the inverse of the linear transformation. Okay, now here we're going to do that for both linear transformations. Here we have 2 by 2 to 2 by 2, because we have here R2 to R2, which is also the same thing here, R2 to R2. In short, let us start with the standard matrix of the given linear transformation. And since it's an element of R2, we have two columns, or in short, it's a 2 by 2 matrix here. How do we determine the entries of a 2 by 2 matrix? The first column would be for all the x coefficients. The second column would be for the y coefficients. And we have two entries here. This would be the first row and second row. Let's start. For our first entry, you have 2x. So you have 2x, and since you don't have y, automatically that's 0. Next here, for our second entry, we don't have x, so that's 0. We don't have also y, that's 0. In short, it's a 0 vector. Okay. This is actually now our standard matrix for the linear transformation. Its inverse, if exists, will follow this pattern here, or this process rather. This is one of the theorems we've learned before. Times you have D, A, negative B, and negative C. Where A here is 2, B is 0, C is 0, D is also 0. However, you don't need to stress too much with this, because we need to check first if it's invertible. That means if this exists, okay, or this entire fraction exists right the way. So if we're going to multiply AD minus BC, you will have 2 times 0 minus 0 times 0. 0 minus 0 is 0. If this is what we also know as the determinant of a 2 by 2 matrix. If our determinant is equal to 0, hence this doesn't exist and the inverse doesn't exist. If the inverse doesn't exist, then definitely all of this will be cut out. In short, our standard matrix of A is not invertible, and automatically we can say that our linear transformation T here is also not invertible. That would mean we cannot show a specific linear transformation that is the inverse of the given linear transformation. This was made possible by identifying that our inverse doesn't exist because the determinant of a 2 by 2 matrix is equal to 0. Let's check if it's the same case with the second here. Again, we're going to show its standard matrix, connect with the inverse, have this form before we could come up with the inverse of linear transformation. Our matrix A here is also a 2 by 2 matrix. X and Y, X for the first column, Y for the second column. The first entry is 0 and 0. Second entry, there's no X, 0. We have negative Y, so negative 1. If we're going to examine again the inverse using this process, D, A minus B minus C, we need to check first the presence of AD minus BC. Our A here is 0, B is 0, C is 0, and D is negative 1. If we're going to multiply that, 0 times negative 1 minus 0 times 0, that's 0 minus 0. We also have a 0 here. Our determinant is 0, hence this doesn't exist. Therefore, our standard matrix A here is not invertible. Consequently, if the standard matrix A is not invertible, we can also say that the linear transformation T is not invertible. This is again made possible by understanding the standard matrix T, or A of our linear transformation T, it doesn't have any inverse, or it's not invertible. In short, for these two examples in this video, both linear transformations doesn't have an inverse. Thank you very much for watching.